This is going to be a system that's accelerating on a ramp, so it's not in equilibrium. We've got a string of negligible mass passing over a frictionless pulley. M1 is 10 kilograms and M2 is 7.5 kilograms. The angle of the ramp is 33 degrees. This is a smooth incline, so there won't be any friction involved at all in the problem. And it also tells us to let down the ramp be the positive x direction. We're asked, with what acceleration will the mass M2 move along the inclined surface? And in what direction? So for the purposes of analyzing these problems, I often recommend unwrapping the situation because the pulley doesn't really matter when it comes to finding the acceleration of a system like this. What we're going to have is we're going to have a force exerted on M1, and it's going to be a gravitational force. That's something we can easily calculate. So let's go ahead and calculate that. Now, the gravitational force pulls down on M1 in the ramp picture. But when I unwrap the system, I'm going to let that force of gravity pull to the left. And it'll be called FG1. Alright, so let's use the mass of it, and we'll find what FG1 would be. It's 10 kilograms. So we're talking about 98 newtons. So this is 98 newtons. Alright, now there's going to be a tension force applied to M1 as well. So this system is not necessarily in equilibrium, so we can't just assume that Ft equals Fg. What I'm going to want to find next is the force of gravity on M2. M2 is a smaller mass, 7.5 kilograms. So let's go ahead and calculate Fg2. It's 73.5 newtons. Okay, but that is not the force that pulls down the ramp. We need to find out what the force that pulls down the ramp is. This is going to be Fg2x. Alright, now how do we actually find Fg2x? Well, we can find its magnitude using the formula Fg2 sine of the theta of the ramp. That's how we had done it before. Okay, so let's plug in. Fg2 is 73.5 newtons. And then we'll do a sine of 33 degrees. That's 40 newtons. Now this is actually going to be the force that gets applied in our analogous system diagram. See, this is just an analogy to the real situation. And the reason why it's useful is because the acceleration we get in the analogy here will be the same as the acceleration of our system on the ramp. All right, so what goes there is Fg2x, and it was 40 newtons. Okay, now the tension forces don't actually matter when it comes to calculating the acceleration of this system. The reason why is the tension forces are going to be equal and opposite. Now, an important question is, can we decide which direction this system is going to accelerate just from the information we have so far? And the answer should be yes, we can, because we've got a larger force here pulling to the left than is pulling to the right. So the one pulling to the left is going to win. That means the acceleration of this system is going to be in a sort of counterclockwise way. Now, if M1 is going to accelerate down, the only way that can happen is if the Ft that acts on it, the force of tension, is less than the force of gravity there. But also, if M2 is going to accelerate up the ramp, the only way that could happen is if Ft, the force of tension that it acts on it, is greater than Fg2x. So with that in mind, we want Ft to be larger than Fg2x. But we also need Ft to be smaller than Fg1. All right, now these are going to be equal and opposite forces. One pulls on M1, pulling it to the right. The other one pulls on M2 to the left. Like, that rope is not going to exert a net force on the system. And the idea is that any force that exists within a system cannot exert a net force on the system itself. All right, so when we go to calculate the sum of the forces, we just want to include the 98 and the 40. But here's where the analogy becomes useful. Instead of just using Fg1, I can put an x on there and now use a sign to keep track of which direction the different forces pull. So see, the 98 newtons in my analogy here pulls to the left, so I would make it negative. The Fg2x here pulls to the right, so I'll keep it positive. Now, when I sum the forces in the x direction, I want to do Fg1x plus Fg2x. Now, what does that make? It gives us a negative 98 and a positive 40, giving us a net force in the x direction of negative 58 newtons. That's something we can use to now calculate the acceleration of the system. We'll use Newton's second law for it. So down here, according to Newton's second law, the acceleration of the system will be the net force divided by the mass of the system. And I'm going to include little x's so that I remember to keep track of the directions. So we're going to put a negative 58 newtons on top. And let's put the total system mass on the bottom, which is the 10 kilograms plus the 7.5 kilograms. The idea being that this net of negative 58 is going to act on the whole thing, all the mass. It gives us a negative 3.31 meters per second squared. Now the negative indicates that our system is going to accelerate to the left. So that means M1 will go down. So M1's acceleration will be down and M2's acceleration will be up the ramp. And this will be our final answer here for A. Now it asks, what is the tension in the string? To answer that question, we have to make a new choice of system. And we can go ahead and grab any of these blocks here. So either one will work. And we'll just analyze the forces on M1. I'll use Newton's second law. And I'm also going to continue to use my analogy here. So the net force in the x direction equals m1 times acceleration in the x direction. Now the net force will be a combination of Fg1x plus Ft on 1x. This force here is Ft on 1 in the x direction. I'm talking about this one. Those are the two forces that act directly on M1. Okay, so we'll get this. Now let's plug in the different numbers. It's negative 98 for the Fg1x. Let's see, we're not going to know the force of tension. Now we want to use the mass just of block 1, so 10 kilograms. And for our acceleration, negative 3.31. Okay, we'll solve this equation for Ft on 1. .9 newtons. Now it's important that this is consistent, and if we were to analyze the other block, we would get the same answer. So let's just do that real quick, just to make sure that it all tells the same story and everything adds up. Okay, so I'm going to pick now M2 as my system. And over here, let's do an equation for M2. For M2, we would say F net on 2 equals M2 times A in the x direction. Now, what forces act on M2? We'll have a tension force that goes in the negative direction, Ft on 2. There will also be an Fg2x pulling it down the ramp. And there we go. So the Ft we don't know. But we do know that our Fg2x was 40 newtons. Our mass of block 2 is actually 7.5 kilograms. And the system will all have the same acceleration. Negative 3.31 meters per second squared. Okay, solve that. Negative 64.8 newtons I think we're off just because of rounding, of course. I could have kept one more significant figure in my calculations, but as you can see, they're the same. And that's good. Okay, so if I was to plug those numbers in here, we'd get approximately 65 newtons and 65 newtons. There we go.